Howdy, folks. Welcome to our last section of Chapter 6. And in our last section of Chapter 6, we're going to be dealing with trapezoids. If you look on our family tree, the trapezoid, as you can see up here, is kind of like the black sheep of the family. The trapezoid, you can see, is offset over here. It does not fall under any of the other parallelograms or rectangles or rhombi or squares that we covered. The kite is another one too that's kind of like that. He's the black sheep of the family. The kite, as you can see, has two consecutive sides side by side that match. A trapezoid, what makes a trapezoid is that it's really basically half of a parallelogram. The parallelogram, remember, had two pairs of opposite sides that were parallel. Well, the trapezoid is only half the quadrilateral that one is. It's only accomplished half of that. It only has exactly one pair of parallel sides on it. The other two sides are not. Okay, so that's our definition, as you can see that I had on this side. A trapezoid is a quadrilateral with exactly only one pair of parallel sides. And then in this picture, I hope you can see, it's the top and bottom here that run parallel. But when you draw these, you are welcome to rotate this, and you could have the left and right be parallel instead of the top and bottom. But no matter how you draw it, the two sides that are parallel, the only two sides that are parallel, are then referred to as the bases of the trapezoid. So you might hear me call this one, for example, the upper base, since it's on the top, and this base down here at the bottom, you might hear me call that the lower base. Okay, now the other two sides on a trapezoid which are not parallel, you can see these two would eventually hit each other if you continue on. Okay, those two sides are both labeled the same way as well. These are bases, and those are both called legs. So it's kind of like like a right triangle, for example, has two legs. So does a trapezoid. But the legs are always the two that are not parallel on a trapezoid. Now every trapezoid then is going to have four angles as well. I'm going to number those in this picture, 1, 2, 3, and 4. And there is some special things going on about some of these angles. If you just use a little bit of common sense here. For example, if I were to ignore that leg and just focus on this leg and those two bases that were parallel, well, when parallel lines are cut by a transversal, notice it creates a pair of same side interior angles. And we learned back in chapter 3 that if the lines were parallel, like the top and bottom are here, then those same side interior angles 1 and 4 have something going on here. And it's not that they're congruent. I mean, you can see that one's obtuse and this one's acute. But instead, it turns out that they add up to 180 degrees. Now, if I ignore this leg this time and draw this one back in, you see it happens again. I got two parallel lines. They're cut by a transversal. So these same side interior angles 2 and 3 also will add up to 180. Okay, but don't assume that's true about all pairs of consecutive angles here inside of this trapezoid. If I draw this back in again, it only works between the parallel lines, or you might say it only works for the same two angles on the same leg. The two angles on the same leg. So 2 and 3 add up to 180, they're on the same leg. 1 and 4 on the same leg, they add up to 180. 1 and 2 would not. Do you see how both of those are obtuse and the lines, the legs themselves are not parallel? So those two would both add up to something over 180, whereas 3 and 4 down here also will not add up to 180. Both of them appear to be acute, so less than 90 plus less than 90 is going to add up to something less than 180. Okay, so be careful. It's only the two angles on the same leg in between the parallel lines that will add up to 180 on a trapezoid. Okay, now I will have some theorems here yet in this section about trapezoids, but the theorems we're going to have are going to be in particular about this type of trapezoid called an isosceles trapezoid. In fact, most of the time when I ask you guys to, if I were to ask you to draw a trapezoid, most people would draw this one. It's very balanced, very symmetric, the same on each side. In fact, what makes an isosceles trapezoid, what gives it its name, is the fact that it has to have two congruent legs. So these two legs have to match in length, whereas up here, I purposely drew this one with different lengths of legs. Okay, so an isosceles trapezoid then, as a result, is going to be very balanced, or you might say very symmetric. In fact, now let's go ahead and give you, we got a couple of theorems that we know are true about the isosceles trapezoid in particular. So I'll keep these in pink, just like I wrote this definition in pink. But our first one is Theorem 614. And Theorem 614 states that both pairs of base angles of an isosceles triangle, or a trapezoid, I should say, an isosceles trapezoid, are congruent. Okay, so, it's saying if it's isosceles trapezoid, then say here's my two matching legs. Okay, and in this picture, not only are those two legs matching, but if I label this A, B, C, D, they're saying that the base angles will match as well. So this angle A down here will match that angle D across the way over there. And this angle B at the top that looks obtuse will match this angle C across the way that looks obtuse. Okay, so in our picture, the opposite angles, the base angles, I should say. The two angles up here at the upper base match, and the two angles at the lower base match. If you remember right, that's very similar to what we already had before on an isosceles triangle. In an isosceles triangle, we said if these two legs match, then the opposite base angles here and there match. So all we're really doing in this case is cutting the top off of this and calling it now a trapezoid and having the top base angles match as well. Okay, so think of it like that. It's like an isosceles triangle that the top got cut off of. They made a cut parallel through there. Okay, there's another theorem, Theorem 615 also, that's true about isosceles trapezoids. Okay, and in this one, if it's an isosceles trapezoid again, if isosceles trapezoid, on this one, there's my isosceles trapezoid again. And again, I'll label it A, B, C, D. But not only are the two legs congruent by definition, but according to this theorem, there's something else that's going to be congruent, and it's the full length of the diagonals. See that full diagonal AC? It's going to be congruent to the full diagonal BD there. Do not, be careful though, do not say that the diagonals bisect each other. They do not. This little part's not going to match that other part down here. That was longer. Okay, I think you could probably end up proving in the end that this short little piece here matches that short little piece, and this piece matches that piece, which in the end, when you add them together, if this matched this, and that matched that, then a double plus triple would equal the other diagonal, double plus triple, see? So the overall lengths do match, but they do not bisect each other. If the diagonals were congruent and bisected, remember that would make it a rectangle. So this is not a rectangle. It's kind of like a rectangle that's been slanted though, in a sense, But they do not bisect, but the overall lengths do match. All right, so that's our theorems for this section. Well, I'm sorry, there's one more. Okay, now the last idea, though, is not specific to an isosceles trapezoid. Okay, so I'm going to erase the whole board here to show you this last idea. And this, like I said, this last idea applies to all trapezoids, no matter whether it's isosceles or not. Okay, so I'm going to switch back to my black colored marker here. I'm just going to draw for you just any old typical type of trapezoid, maybe one that looks like that, where this top and bottom run parallel to each other. Okay, and I'm going to call this one X, Y, Z, W. Okay, now this last idea, I'm going to show you first of all what's called a median. Median. Okay, and it's kind of like what it sounds like. The word median means something that's going to run down through the middle. Okay, and a median is a segment that we could create in a trapezoid like this, for example, by finding the midpoint right in the center of each leg. So see this leg YX? Let's say right there's the middle, splitting that in half. And let's find the middle or midpoint of this leg as well, splitting that into 2 equal halves. And if you join the 2 midpoints, that's the median. Okay, so the median is simply a segment that's joining the midpoints of the legs. Segment joining the midpoints of the legs. All right, so when you make a median like that, our last theorem that I want to show you here, which is listed under your postulates and theorems as theorem 616, refers specifically to that median, and it says that 2 things will be true about that median. Okay, and your gut instincts might be kicking in at this point. You might notice, first of all, for example, that the top and bottom run parallel, and when you join those midpoints, this segment will run parallel as well. Okay, so according to theorem 616, okay, when you create that median, okay, it'll be parallel to the bases that were already parallel in the first place. So maybe we'll label this Q and S here. So according to theorem 616, that median QS should now be parallel to both the YZ at the top and the XW at the bottom. Okay, so the median's parallel to the bases. But that's not the only thing that's true about it. Okay, according to theorem 16.6, not only do all these run parallel, but there's also something true about the length of that median. And before I go into that, let me just point out real quickly then, if these all run parallel, keep in mind that parallel lines, like I've said before in our 10 Commandments, lead to congruent angles. Remember, chapter 3 was all about that. So you should have all kinds of matching angles. Like, see this angle and this angle? Okay, if these run parallel, that's a pair of corresponding angles that would match. You could do it again. Here and here. Or there and there. Or even here and there. Okay, so you have all kinds of corresponding angles that would match with the parallel lines. Okay, now moving on to the length of the median. Something special about it as well. Okay, its length, if you look at it, notice its length falls somewhere in between the 2 bases. See how this base seems to be longer, whereas the one up here seems to be shorter. You know, I like to think of it, it's a lot like the old tale of Goldilocks, you know, where the porridge was too hot, too cold, and then she found the one that was just right in the middle. Okay, that's what's going on here as well. That median is a middle ground. It's right in the middle length between these 2 bases. Okay, so for example, in this picture, if I told you that this base up here, if I said it had a length of 8 units long, and this base down here, let's say, was 14 units long, then your median on this problem, your median would have to have a length that is the average of those. So you would take the 8, the 14, you would add them and divide by 2. You're going to find their average, their middle ground. Okay, and 8 plus 14, as you can see, is 22. Divide that by 2 and you get 11. So 11 would be the length of the median. Okay, it's exactly in the middle. All right, so with all of that in mind now, let's go ahead and try some problems here. So I'm going to clear my board and jump right into some. All right, so for our first one here, let's draw a picture of a trapezoid here, complete with diagonals, and I'm going to label this A, B, C, D, and in here we'll call that point E. And in this picture, I'm going to mention that this is an isosceles trapezoid. Okay, that's an isosceles trapezoid for these questions. So my first question is going to be this. Is AC equal to BD? AC, that diagonal. BD, that diagonal. Okay, are they equal? You should be able to tell me yes, they are, because remember we just had a theorem that stated that in an isosceles trapezoid, the full length of these diagonals are equal. Okay, so that is a yes. I want to say it was theorem 615. Okay, but I want to ask you a few more questions yet about this picture. Here's my next one then. Is segment AD congruent to CB? Okay, is AD congruent to CB? You should be able to tell me yes. By definition of an isosceles trapezoid, by definition right away, you know those two match. Okay, and that's why it gets the name isosceles. It has to have two matching legs. Okay, next question. Segments CA and BD bisect each other. Do segments CA and BD bisect each other? So do the diagonals bisect one another? Okay, you should be able to tell me on this one that our answer was no. Okay, remember we just got done talking about that. The diagonal lengths are the same length, but they do not bisect. If they were the same length and bisected, then it would be a rectangle. Remember, a rectangle is one of the only quadrilateral shapes where the diagonals overall length there matches the overall length here, and they cut each other in half. They bisect. Okay, this one they do not. Remember I showed you earlier, this top part there would match this top part. This bottom part would match that bottom part, but that does not mean they're bisecting, because those two halves don't match, and those two halves don't match, see? So it's not going right, that's not the midpoint. That's not right in the middle, whereas this is. That point's right in the middle of both diagonals. Okay, let me start with a new picture for some more questions here that I want to ask you. Okay, in this picture again, This is an isosceles trapezoid. Okay, notice though, to try to confuse you a little bit, I drew the parallel bases running up and down like this, you know, from side to side instead of the top and bottom. All right, so I'm going to label this as Q, E, U, D, F, A. All right, first question. If QU equals x squared and AD equals 16, let's find x. All right, now, by the way, this is an isosceles trapezoid, and EF in the picture here is the median. And EF is the median. All right, so an isosceles trapezoid, I want you to keep in mind, already has, it's called isosceles because it already has overall legs that are going to match. So QU, that full length QU, is going to match the full length DA or AD. Okay, so in this problem, really, we could kind of ignore that median down the middle. We're looking at this entire length and this entire length. Okay, and on an isosceles trapezoid, like I said, those match. So I know that these two are equal to each other, so I can just say x squared equals 16. Okay, now be careful on a problem like this. Anything with a power of 2 technically has 2 answers. So if you're just going to do a square root at this point, believe it or not, there's 2 answers. It's not just 4. It could also be -4. Just think about it. If I plug a -4 in here for the x squared, negative times a negative is positive. So -4 fits in there and still gives you 16. So x could be either one, +4 or -4. Okay, the problem with the calculator, when you do a square root on a calculator, it always just gives you the one answer, the positive answers. But way back when you first learned about doing square roots, they should have taught you that there's actually 2 possibilities. All right, so there's your answer on that one, 4 or -4. I want to use the same picture, though, again for another problem here. We'll change it up a little bit this time. If the, let's do this. Let's say if QE equals 17, find the length of AF. I'm going to put this back in again. Remember, that is the median. Okay, but they're saying if this length QE right here equals 17, they want us to be able to find AF, this one down here. Okay, again, remember it's isosceles, which means the overall lengths match. And a median, by definition, a median connects midpoint, so I know those 2 halves match. Goes from midpoint to midpoint again, splitting those. So if this overall length matches this overall length, and these are right in the middle of each of those, then all 4 of these match. So this is 17, that's 17, that's 17, and that's 17. So AF is just 17. If they had asked for AD, you would have added both of them together. 17 plus 17, or 34. Okay? All right. Just try one more yet here using this picture. On this one, use 17s from the last problem. Okay, but on this one here, you'll notice that QUA, that angle QUA, so this angle down in this corner is 62 degrees. And they want us to find angle ADQ. ADQ is this angle clear over here. Clear across the way from it. Okay, now, be careful. It's not 62 again. You know, your gut instinct should help you. 62 here, that acute angle is 62 degrees. This one looks obtuse. So, you know, not that that proves anything, but it's a good way to guide you. You know, let your gut instincts guide you. But in an isosceles trapezoid, we did have a theorem today that said that the two base angles, the two angles on the same base, those will match. So not only is this 62, but I know this one is 62 down here. Okay, that was our theorem 614, I believe, is what that one was. Okay, but then we also had one other idea today that was not a theorem, but it was something that was true about all trapezoids. And in all trapezoids, and for this problem, we could kind of ignore this median, by the way. But in all trapezoids, the two angles on the same leg, so these two angles here, the one I want to find and the one I already know down here, 62, they're in between parallel lines, so that makes them same side interior angles, and I know that means they should add up to 180. So if I take the 62 away from 180, that's going to leave me with 118 degrees, and that's the measure of the angle we're trying to find here. That angle D there, ADQ. Okay, not only is that 118, but you could actually go on and find all kinds of angles in this picture. This would be another matching 118 then over here. We could even find the angles on either side of this median. You know, this 62 means that this right here should be a matching 62 because those are corresponding angles. And this 118 corresponds with this angle. So that's 118. You know, 62 here, 62 there. 118 here, 118 there. So every angle up here is going to be one of two measurements, either the 62 or 118. But again, that only works for isosceles trapezoids, where you can take everything from this side and do a mirror image of it down here, from one leg to the other. Okay, so you'll have problems like that I'll have you do. I also want to try some other ones here that deal a little more with those medians that we were talking about earlier. You know, what if I gave you a problem like this? And if I say, all right, here's the midpoint of this side, I'm going to connect it over here to the midpoint of that side, which then, of course, makes this a median, running right down through the middle. Okay, and this top and bottom are parallel, so this is a trapezoid. Okay, it doesn't have to be an isosceles one. Okay, we're just going to say it's a trapezoid. Okay, and what if I told you, for example, that this top side up here is 12 in length, and let's say I gave you the median and said the median was 15, and I wanted you to find the last base down here at the bottom. So the top base, upper base is 12, median is 15, find the lower base. Now you can approach this one in two ways. If you remember right earlier, theorem 616 talked about how a median is, its length is the average of the bases. So you could actually do this. You could say 12 plus the x divided by 2, you know, this base plus that base divided by 2 has to equal the median, 15. So this is an algebraic approach to this problem. And then solve for x. So you multiply by 2 to begin with just to get rid of the fraction. So we've got 12 plus x, and whatever you do to one side, you got to do the other. So I got to multiply that times 2 to get 30. And then subtract the 12 from both sides. Okay, do you see that that would give you a length of 18 for this bottom line? So this is 18. Okay, another way though to find that that's a little bit quicker, you know, since this median's exactly in the middle, that means as you step down to this and then as you step down to this, each time you step down to each of those segments, they're all evenly spaced such that if you look as I go from 12 to 15, do you see that that's a drop of 3? You know, if you take 3, or I should say an increase of 3. So 12 plus 3 is 15. And if I add another 3, look what happens. 15 plus 3 is 18. So that's a little bit easier way, I think, to do it. If just one of these values is missing, whether it be the top or bottom value, just follow the pattern, you know. Add 3, or if it went the other way, you could say subtract 3 and then subtract 3 again to get that one. Now, if the middle one's missing, though, you're going to have to do the average and calculate it. Okay, now, what if I gave you a median problem again, only this time I made it a little more difficult by giving you something that maybe looks like this. Let's say again that's a trapezoid with this top being parallel to this bottom. Let's say there's the middle of that leg, and I'm going to connect it over here to the middle of that leg. So that's a median. Okay, and what if I told you this up here was 3x minus 1, that upper base. Let's say the median I give you as being 10, and the lower base is 7x plus 1. And I said, okay, find x. Or for that matter, you could even, after finding x, plug it back in to find either length of the bases. Okay, on a problem like this, you're going to have a hard time doing that shortcut like I showed you, where you look for a pattern or anything, because I don't know this one, I don't know this one, I only know the median, you know, I only know one of the 3. So this one, you're going to have to take that algebraic approach where we just simply say that the median should be the average of the bases. So that means 3x minus 1, it's supposed to be a 3 there. That top upper base and the lower base, if I were to add them together and divide it by 2, I'm doing the average of the bases, it should equal the median. So it should equal the 10. Okay, so like I did on the other problem, when I approached it the algebraic way, this 2 causes some issues. It makes one big fraction out of this. So I'm going to go ahead and multiply this by 2 so that it cancels that out. But whatever I do to one side, got to do to the other. So that's now a 20 instead of a 10. And then over here, see in the top of this, it's like a sheriff and a deputy, right? We could take those and combine those. 3x plus 7x combines to give you 10x. Same with the positive one and the minus 1, but they just combine to give you 0. So now the problem simplified an awful lot. Now I just have 10x equals 20. I divide by 10 on both sides, and look, x is 2. Okay, you could always go back and plug that 2 in even and find out what each of your lengths are. You know, here 2 times 3 would be 6. 6 minus 1 is 5. And then here 2 times 7 would be 14, plus 1 is 15. So this one skipped up by 5s. 5, 10, 15. Okay, but that's the only way to get the x, though, was to do this algebraic approach like that. Okay, speaking of algebra problems, there's one more I just want to try and throw out at you. Now this last one has nothing to do, though, with a median. Okay, but on this last one, this is going to be an isosceles trapezoid. So we're going back to one of those, an isosceles trapezoid with 2 matching legs. Okay, so let's say that our isosceles trapezoid is labeled as ABCD. And let's say that angle B over here is 108 degrees, and angle D down here is labeled as 7x minus 5. And of course, being an algebra problem, I'm going to say find x. All right, so be careful. It is isosceles, which means it does have matching legs, but that's not all. Remember, isosceles trapezoids also have matching base angles. So be careful. This, like down at this base, this angle would match this one, not that one. But that angle at the top there matches this one. So I could transfer that 108 over on this side and call that 108. And now do you see why I did that? My next step is going to say that these two angles, they do have something special going on. Not just because it's isosceles, but in any trapezoid, two angles on the same leg in between the parallel bases. You know, if I erase this one, see, you can focus on it now. There's a transversal crossing the parallel lines. That's a pair of same side interior angles, which means that they should add up to 180. So I know 7x minus 5 plus the 108 equals 180. Or as a shortcut, you could just go right off the bat and say that the 7x minus 5 would be the rest of 180 after taking the 108 off of this. You know, if I did that first here, do you see that leaves you with 72 degrees is what this angle should be. Okay, but you add your 5 to both sides, divide by the 7, and we find that x is 11 on this one. Okay, so if I draw that back in, you know, if they give you opposite angles like that, be careful. They're not equal to each other. But the same base angles, like the upper base angles here, match. And then we could say these two consecutive angles on the same leg have to add up to 180. All right, I think that should be enough practice to prepare you for your homework assignment. Oh, wait, I'm sorry. I forgot one more problem. Okay, I'm going to show you one that's similar to what you're going to have on your homework as well. And then I'll be done. Okay, on this last one, it's going to involve an XY coordinate plane, and we're going to have a trapezoid pictured here. Let's say that, we've got one point here at the coordinates 3, 1. Another point down clear over here at 10, 1. That's C, this is D. Up here at 5, 9 is a point F. And a point E then that's going to be over here at 7, 9. If I connect all that, okay, that's going to form a trapezoid, and there's a reason I know that that is a trapezoid. For example, see how this went 5, 9, 7, 9, both the 9s match, so that's perfectly horizontal. So that top base right there runs parallel to this one as well. Because notice that one's 3, 1, 10, 1. It's perfectly horizontal as well with the 1s matching on the y values there. So I do know it's a trapezoid. Okay, but on a problem like this, they'll ask you different questions. Like one of the first questions they might ask you is, if I were to insert in here a median, you know, if I want to make sure that this was a median of our trapezoid, we're going to label it as GH. Then they're going to ask you to find the coordinates of G and H so that that would be a median. Okay, so you're going to have to find G's coordinates and H. Now, if you remember right, a median is created by connecting what special point here to what special point there. Okay, if you guess the midpoint, you are correct. That needs to be exactly in the middle of that leg. This one needs to be exactly in the middle of that leg. Okay, so really what they're asking you to do is calculate the midpoints. Okay, if you remember right, to find a midpoint means you're going to have to average together the x values and average together the y values to get the coordinates of your new midpoint. Okay, so that's what we're going to do here. I'm going to give myself a little more room though. So on G, I want to average together the x coordinates of 5 and 3 on this leg. So 5 plus 3 divided by 2. And for the y values, 9 plus 1 divided by 2. So G's coordinates would be at, well, that's 8 divided by 2 is 4. Y's value would be 10 divided by 2 or 5. So that's located at 4, 5. Okay, H, we could do the same thing then. We're going to do the midpoint of these endpoints. So 7 and 10 were my x values. Add them and divide by 2. 9 and 1 are the y values. Add them and divide by 2. So that's 17 divided by 2 is 8.5. 10 divided by 2 is 5. So this one's at 8.5, 5 for its coordinates. All right, now one of the other questions they may ask you on a problem like this, in fact on your homework there'll be one like this, they will ask you to verify the following. Verify that GH equals 1/2 of, that's supposed to be E by the way up there, 1/2 of FE plus CD. Verify that GH is half of FE plus CD. Now verify is just a fancy way then really in this case of saying check and see if this is true. Okay, so you're going to have to find each of these lengths. You have to find GH, FE, and CD, and we're going to have to plug each of those in here. Okay, and we're going to check and see if this equation works. Now the beauty of this is, normally you'd have to use the distance formula to find these, but if they run perfectly horizontal, like FE here runs from 5, 9 to 7, 9, the 9 stays the same. So you can see it really just runs from 5 to 7, so its length is 2. So there's FE, that one's 2. Okay, GH does the same thing. It runs parallel with these other bases. Look, it goes from 4, 5 to 8.5, 5. The 5 stays the same, so it's really just going from 4 to 8.5, which would be a length of 4.5. So there's our GH. Now all we need to do is find CD. 3, 1, 10, 1. The 1 stays the same, so it's really just going from 3 to 10. That would be a length of 7. And what do you know? 2 plus 7 is 9. Half of 9 is 4.5. Oh, see, it checks. If you bring that down, 4.5 does in fact equal 4.5. So we have verified that it works. Okay, now that should finally prepare you for your homework, which, as I was beginning to mention, is going to be on page 325, problems 16 through 32. Okay, if you've been having any difficulty on any of these sections lately, don't forget I've been holding office hours. Monday, Wednesday, and Fridays. You can join me on the Zoom app at 3 o'clock on each of those days, Monday, Wednesday, Friday. And that'll help prepare you because that's our last section of chapter 6. So our next stop here is going to be to do some review. I'll give you an assignment where I'll give you a chance to do review problems to prepare you for the test and the test itself. Okay, so get in contact with me either through email or remind if you do need help outside of office hours. Okay, thank you.